Welcome to MCV4U, Calculus and Vectors. For our first topic, we're going to take a look at limits and continuity. Limits will give us a specific way of describing what we mean for a function to approach a specific value. In this case, let's take a look at the function f of x equals x squared. Suppose we wanted to answer the question, what does it mean, the limit as x goes to 2 of x squared? Well, in order to determine this, what we're going to do is we're going to follow the curve along the function, approaching the x value 2 from the left, and we're going to do the same thing from the right. We'll notice that in this case, if we follow the curve along the function, approaching x equals 2, we approach the value 4. We'll notice that if we follow the curve from the right, we also approach the same value 4. This, in fact, will be our definition for limits. We will say that if the limit of f of x from the right is the same as the limit of f of x from the left, then the limit exists and will equal the value that we approached. So in this case, we write this as the limit as x goes to 2 from the right, from the positive side of f of x, equals the limit as x goes to 2 from the left, noted by this negative sign, will in fact both equal 4, and therefore we will say that the limit as x goes to 2 of x squared equals 4. Notice, however, I didn't specify in this definition anything about what's happening to the function at 2. We know intuitively that it makes sense for this limit to be 4, because if we were to plug in 2, we would in fact get 4, but that's not a requirement in our definition. All that we require for a limit is that the function get close to that value from both the left and the right. So let's take a look at a second example here. In the example f of x equals x squared minus 1 over x minus 1, we know intuitively here that there's a problem with the domain. If we were to plug in 1 into both the numerator and denominator, we would get 0 over 0, and we would expect a restriction to be x cannot equal 0. If we were to graph this function, we would in fact see that there's a hole in the graph. So what does this mean in terms of the limit? Well, let's take a look over here. We write this as the limit as x goes to 1 of x squared minus 1 over x minus 1. And we can solve this problem by factoring. If we factor both the numerator and denominator, we can cancel the common factor, in this case x minus 1, leaving us a function that no longer has a denominator that will cause us algebraic issues. Because I said that we don't actually care about what's happening at x equals 1, we can ignore the restriction, and now if we plug in the value x equals 1 into this function, we can say as x goes to 1, the value will be 2. Now let's check our intuition. If we follow the curve from the left, as we said in the previous example, we'll notice that this function is in fact getting close to 2. And if we follow the curve from the right, we'll notice that the curve is in fact getting close to 2. So again, our left-hand and right-hand limits both exist and equal the same value, thus the limit exists and is equal to 2. Next, let's consider what happens when we apply limits to composition of functions. Suppose we have a function f of x, and the limit as x goes to a for f of x exists and equals L. L needs to be a finite number here, 2, 3, 4, 0. And we have the same thing being true for another function, g of x. We have the limit as x goes to a of g of x equals m. So again, any finite number. What would happen if we took the limit as x goes to a? Notice we have the same point that the limit is approaching for both functions, and we add these two functions. What would we expect the limit to be? We will discover that the limit of f of x plus g of x will be L plus m, and the same thing will be true as if we take f of x minus g of x, we'll have L minus m. This is a useful property that we'll make use of shortly. We'll see that this also holds for other algebraic operations. If we take the product of f of x and g of x and take the limit as x goes to a, then the limit will equal L times m. And the same thing will be true for f of x divided by g of x, with the extra condition that m cannot equal 0. Let's take a look at an example here. If we were given a function, x squared plus 2x plus 1, we've already seen in previous examples how we can figure out what the limit of x squared is individually, and similarly we could do the same to figure out what the limit of 2x and 1 would be. Using these new rules that we've defined, we can now apply our first limit rule to this function to determine what the limit will be of this composition. So we can expand the limit across this sum, getting the limit as x goes to 2 of x squared, plus the limit as x goes to 2 of 2x, plus the limit as x goes to 2 of 1. We can now plug the value of x that we're interested in, 2, into each one of these terms, and figure out the individual values and sum them up using our first rule. And in this case, we would get 9. Next, let's take a look at continuity. We've probably thrown this term around a few times already. Intuitively, what we mean by continuous is if you can draw a function without having to lift your finger, that function will be continuous. We've seen examples of both continuous and discontinuous functions in the past. So say our blue curve here is the curve 1 over x, and we know it has this vertical asymptote. It would make sense for this function to be considered discontinuous because I can't follow the curve on both sides without lifting my finger. In our final example of discontinuity, we'll have h of x, our red curve here, and it has a hole in it. I can't follow this curve without lifting my finger. We'll call this a point discontinuity if we have a hole in it. We'll call this an infinite discontinuity if it has a vertical asymptote. But let's give ourselves a more formal definition for this. Formally, we can describe continuity as this equality. If we have the limit as x goes to a of f of x equals f of a, then a function will be continuous. Well, what does this look like? Well, we saw in our first example, when we were talking about the function x squared, that when we approached the specific value from both sides, the limit exists, and we also had the value at that point be the same, the right-hand side. In our second example, which was similar to h of x, we had the limit exist, but there was no point here. So f of a didn't exist. When this condition fails, we'll say the function is discontinuous. And we'll notice that this would also be true for our blue curve, 1 over x. If we plugged in 0 for x, we would have an undefined point. We'd have 1 over 0. So again, the right-hand side would fail, and we would not have continuity. If this condition, however, holds, so f of x, the limit as x goes to a of f of x is equal to f of a, we'll say that the function is continuous. And if this is true for all values of a, so in the example of our black curve, it doesn't matter what point I pick on this curve, this equality will always be true. We'll describe f of x as being continuous. We'll see some more examples of this in our homework. Good luck, guys.